All right. Can you start? Should we start? Okay. Okay. Yeah. So yeah. Today we're gonna review Source 361. So it'll be posted on the YouTube clip in the form of a YouTube clip. So you can review the clip later. But let me know if there are questions, okay, during the session. Okay. So the most important topic in Source 361 was linear regression, right? So to start with, what linear regression is? What is regression? Yep.
So I can tell that I can talk about the linear regression, but I can
Just regression.
just regression. Yeah. Linear regression is that to use linear equations to estimate the fraction of the interest by using regression.
Mm-hmm.
So not
But the
simply
question is, what is regression?
what is regression?
Uh-huh.
I just know regression is mathematical tools to estimate.
To what? To what?
estimate.
Estimate what?
Oh, the causal relationship.
Not necessarily. So there is a lot of purposes of regression, and because estimate causal relationship is one of them. Actually, so
Correlation.
what? Sorry.
Correlation.
Sure, but then I would phrase the definition in such a way that it's basically regression is basically there's transforming the outcome of interest or the variance of the outcome of interest into certain functional form. So that's why it's called regression. So it's regressing the variance of the outcome of interest into a certain linear, certain functional form. Okay. For example, let's say we have the outcome of interest income. Okay. This is y variable. All right. And then this is the y variable's mean, or mu y. Okay. And then there is variance of y, or standard deviation of y. Okay. So there's so a variable has certain variance, right? So we are trying to find a systematical pattern by regressing the variance, this variance of outcome variable into a functional form. And linear regression is a regression when the when the functional form is a linear one. Okay. So there is. There are observations like that, and then this observation should be right here, right here, right here, like that. Okay, so basically, it's explaining or regressing the variance of the outcome into a linear form based on certain characteristics such as or x variables. Good. Any questions?
I remember if we can transfer any nonlinear equations to a linear ones, it's still a linear regression, right?
Right. But not. So we're gonna cover nonlinear regression in statistics 2, which is exemplified by probit models or logit models, and then in this case, it's more of a not necessarily linear regression, but if you are talking about putting logs into into X variables and stuff like that, then yeah, it can be a linear regression. But the interpretation gets a little bit trickier in that sense. Yeah. Good. Any questions? Nope. All right. Good. So there are two components that are really important in linear regression. The first one is predicted value or predicted expected value. It's a little bit redundant, but predicted value. Okay. Given certain X value. Okay. And the second one is how much variance is explained or not explained. Right? So we're trying to regress the variance of the outcome, right? But then the question is, how much of the variance was explained by the linear regression line, right? So the first component is noted as this one, the expected value of y given x is certain number x. Okay, good. So this is the predicted value of y. We're predicting the value of y given the number x right here. So according to the linear form right here, linear functional form right here, when x variable's value is x, the small x, then the predicted value would be right here. Okay, good. And then the other component is basically how much variance is unexplained after the regression. So after some linear regression, after running the regression model, you have some unexplained components, right? You are averaging all of the unexplained components out and then consider it as how much variance is not explained. Great. Is that clear enough for the verbal narrative of the regression? Okay. Model? All right. Okay. All right. In the population regression model, the regression line right here is noted as yi is beta 0 plus beta 1 xi plus ei. Okay. The outcome right here is the linear combination of beta 0, or the intercept, and the slope multiplied by x plus ei, or residual. Good. Or error. So beta 0 is the expected value or the predicted value of y when x is 0. Good. And then the slope right here is whenever x increases by 1 unit, and then the predicted value of y increases by beta 1. All right, good. And then ei is basically the difference between the predicted value and the observed value. Good. Any questions? Nope. All right, good. So predicted value is actually noted as this equation. This is the predicted value of yi. The predicted value for the yi observation. Based on the level of x that I has. When the ith observation has the value of small x for the value of the variable x, then we predict that the y would be right here based on the linear regression form. Any questions so far? Straightforward or good? And then why would there be hat right here? Anyone? What does a hat mean? What does the hat? Yeah.
Is it just the annotation, the notation for predicted?
Yeah. So it's estimated by the linear regression form. So that's why there is a hat. Okay. In this case, let's delve into more of a formal mathematical notion. Okay. E plus yi, expected value of yi is beta 0, expected value of beta 0 plus beta 1 plus xi plus ei. Right? And then this becomes beta 0, beta 1 multiplied by exi, expected value of ei, which becomes Am I making any sense so far, or doing great? Okay, good. All right. Did you understand the transitions right here, or?
What is MX?
Oh, mu x. Sorry, this is the mean of x variable. Yeah, because this is exy. So the expected value of y here is actually the predicted value of y when x is mu x, or the average of x variable. Okay, does that make sense? So this is called marginal expected value of y. Can any of you tell me why this is called marginal expected value? What does marginal mean?
Marginal means is that with every unit of x increase, so how much does y increase? So
Sorry.
by unit. Sorry.
No, it's totally fine. It's totally fine.
Yeah. Just cannot express it in English currently. Sorry.
No, it's totally fine. Can you tell me like what a margin means though?
Yeah, my undergraduate major is economics, so I remember some marginal is just like with so how many quiz do the outcome have by any by the increase of units of x based on the given number of the outcome.
Mm-hmm.
Yeah.
Yeah. It makes sense. So actually, good answer actually. So the word marginal actually comes from the word of margin in a table. So let's say, for example, there is cross table of men, female, male, person of color, white, and then we're just counting people in the sample, for example. 10 people, 20 people, 30 people, 40 people, all right? And the total would be 30 for person of color, right? So this is at the margin right here. Margin of the contingency table right here, okay? So in this case, we are not considering the gender of the person in the counting. So in this case, we're not conditioning on anything. We're just looking at the personal colors and how many people of color are there in the sample. Good? But then we can condition on male respondents in the sample. And the conditional sample size for people of color would be 10. Does that make sense? So there is a difference between marginal and conditional. So marginal means aggregate in a sense. So there are different ways of usages in the word marginal in the statistical or mathematical world. For economics students, it's more of it has a slightly different connotation, but for statisticians, it's more of a margins at the of a table. It all comes from the same source of origin, but then the usage of the word margin can be a little bit different depending on the context. But in this context, it's more about aggregate. Okay, so when you Google some stuff to really know what's going on in the statistical world and stuff like that, and you might come across the word marginal, and then I think this analogy would be really helpful in that sense. Anyways. And let's look at the conditional predicted value. This is the predicted value of yi given x is xi. Okay. So it would be the predicted value on the regression line, right? So this is conditional expected value or predicted value or conditional expected value, sorry, of y given x equals xi. This is also noted as yi hat. Okay. Any questions? Nope. All right. And for variance of yi, would be variance of beta 0 plus beta 1 xi plus ei, right? So beta 0 is a number, so it doesn't have any variance, right? So you can ignore this part. And then this becomes beta 1 squared, the variance of xi plus variance of ei plus 2 beta 1 covariance of x and e. Do you follow that part or no? Or good? Let me know if you have problems with that. Okay? So in this case, this part is actually assumed to be 0 in linear regression. Okay. The error terms are not correlated with the x variable. Okay. This is an assumption. All right. So what it does, is basically we can so by the linear predictor, we are decomposing the variance of y into the explained part because we know variance of xi, right? This is the explained part of the variance, and then this becomes unexplained part of the variance. So the purpose of linear regression is basically decomposing certain raw variance right? Of the outcome of interest. And then we are systematically explaining this variable's variance into the explained part, and we're decomposing this the variance into the explained part and then unexplained part. Does it make sense? Via the linear predictor. So that way we have a better understanding of what's going on and what is driving the variance of outcome. Does that make sense? Any questions with that or? Nope. All right. So in a way, the next point is about the conditional variance of yi. This is the conditional variance of yi given x is xi, right? We know, so xi is basically fixed to a certain value, right? Whatever value that value is, right? So the variance of xi would be 0 in this case, because it's fixed to be a number. So it has no variance now. Does it make sense?
Yeah.
Okay. So that way, it is also assumed to be 0. So this is EI. It is actually noted as sigma hat squared. So this part is sigma hat. Does it make sense? It is unexplained variance after running the regression. And then the distribution of the residual would have the variance of this one, unexplained variance. So the purpose of the linear regression, is to decrease this part, this unexplained part, from this raw wide variance of y. Does it make sense? So we have this is before running any regression, right? So this income variable has no understanding. We don't have any understandings about the income, how income changes and according to what and stuff like that. And by running the regression, we have a relatively clear understanding of what's going on based on what drives y based on x, as well as now we have a clear understanding of what's going on, then the unexplained part would be decreasing as a result. Does it make sense? Am I making any sense? The narrative behind the linear regression? Any questions? Good or bad or? Yeah.
I think because you're writing in a small space, I might have lost track of what equals what
Sorry.
at the end of that piece. So variance of yi given xi equals variance of ei.
Right, residuals variance. So each residual has a certain distance, right? And then you are, so this is the residual, right? For all observations, it has residuals, and then you are calculating the variance of that. It would be 2 or -3 and +1 and stuff like that. You are making a variable out of it, and then you are basically calculating the variance of it.
Okay.
So that is the unexplained part of it, because even after regression, you did not precisely predict what the y would be located at. And then that's the residual. Does that?
Yeah, conceptually, when you say it makes sense. Sometimes paired with notation. I got a little fuzzy with the notation, but
Oh, okay.
conceptually, it's good.
Okay, good. Yeah. Yeah. And then this is also noted as sigma squared. Yeah, sigma hat squared.
I have a question.
Okay, yeah.
Yeah. I mean, if the sigma hat is defined as the residual errors, I think it may be confusing to define the variance of EI to be the sigma hat of sigma hat squared. I think it's maybe confusing. Yeah.
Okay.
Because
So
maybe we should change the mathematical expression of the sigma. I think
Okay.
it should be the sigma hat squared.
this one?
Yeah,
How about this one?
yeah, I think it's good.
Okay, sure. This is the error terms squared. Error terms variance, basically. Sorry, for hats, it's a
Yeah,
sample one actually. So for the population regression model, there's no hats.
I just said the hat is really confusing.
Oh, okay, but in sample regression model, there would be hats.
That'll be right.
Okay, good. Any questions? Am I making any sense or? No? One thing I would make a note about is basically X and E are assumed to be not correlated or independent. Okay, and here is E is a random variable, not actual numbers yet. Does it make sense?
Yeah.
Okay. So if you run the regression, and then and then you calculate all the residuals, and then if you calculate the correlation between X and the residual variable, it'll always be 0. Because linear regression was designed to have the correlation between X and E to be 0. Not because this is actually what happens in the society. Does that make sense? So it is assumed to be 0. So that's why in your data, after running the regression, it'll always be 0. The actual numbers of E and actual numbers X's will have independence to each other. But this is purely because it was assumed when correlations or regression coefficients were estimated. Does that make sense?
Yeah, because it is original least square, so it is.
Yeah, I'll get
really-
to that. Sorry.
Yeah, it is.
I'll get to the part in a minute. OLS regression, OLS estimation. But for now, let's not talk about that for now. Okay, good. Yeah. All right. Yeah. And then now we're talking about sample regression model. And yi is beta 0 hat now. And then this is beta 1 hat and xi plus ei. And now it has hat now. And it becomes x over y bar. Because y bar means the sample mean of y variable, And then this is the sample standard deviation of y variable. Okay? They're all, this is the unconditioned variance or standard deviation of y for sample. Does that make sense? Good. It has hat because it's a sample and it's estimated from that sample. Good. And then beta hat 0 and beta 1 hat. It also have hats because they are estimated from the sample at hand. Good. And now also yi hat becomes this one. So you see three different hats, right? But then the meanings of these hats are slightly different because this hat means estimated or predicted by the linear predictor. But these hats mean that they're estimated from the sample at hand. So they all mean estimated, but then the sources of estimation are different. Does it make sense? Yeah.
When you say why, does why I had is that one's different? Just say that one more time.
Oh, yes. So compared to population regression model, which has yi, beta 0, beta 1, this one, it didn't have hats, right? But now we're using sample, right? So we don't know what beta 0 and beta 1 for sure, right? Now that we have sample, okay? So we are estimating, we're inferring what beta 0 or what beta 1 would be based on our sample. So it becomes hat. There's hat. Because of that, we're estimating. Good. For this one, it is also a hat, but it is estimated based on the linear predictor. Does it make sense? The sources are different. Yeah. So this is one of the things that confuses students a lot. So I think it's better to let that clear. Let that clear. Okay. So before so for this one, in this case, it would be sigma hat, right? Because it's also estimated from the sample at hand. See the difference compared to the population regression model? It has all the hats because we have one sample and we don't know the population, so we are estimating or inferring what the actual beta 0 or beta 1 would be based on our sample. Good? All right. Good. Before moving on to the actual estimation process or estimation formulas and whatnots, let's talk about the basics of inference first. So we do have population right here, right? But then we cannot say survey all the people in the population. This is not simply feasible, right? So that's why we are drawing a sample. Okay, good. And we are inferring parameters or numerical characteristics of the population. For example, mu, sigma, or beta. This is the population mean, population standard deviation. And this is the population regression coefficients. All the things, all the numerical characteristics of the population of interest. And we are, but then we don't know this for sure, so we are obtaining statistics or numerical characteristics of the sample, which is sample mean, sample standard deviation, beta hat, or estimated regression slope. Does that make sense? Yeah. So and then we need a series of assumptions to make an inference about the parameters. All right. This is the basics of inference. Okay. The first assumption is unbiased data generating process, which we will cover a lot during the semester. I mean a lot. So I'll just let that just set aside for the future sections. And the second is patterns of sampling error. What is a sampling error?
So you cannot have your sampling randomly.
You are having your sampling.
I mean,
Uh-huh.
yeah, you should choose your sample
Uh-huh.
by random.
That is a sampling, right? That is a random sampling.
Yeah.
Uh-huh.
So a random sample.
So what is a sampling error? Anyone?
I guess difference between statistics and parameters.
Yeah, exactly. So sampling error is precisely because we don't have all the people in the population. We happen to pick some different people compared to the population, or all the people in the population on average. Good. So we happen to have sample all males, or we happen to have sample all white people from the population. Does that make sense? By pure chance, this is a patterned error, but then this is not biased in a systematic way. It can happen. It can so compared to this, depending on the sampling error, your regression coefficients can be really large or really small. There is no systematic way of bias to drive one way over the other. Does it make sense? Bias is more of a systematically affecting the regression coefficient for one way over the other. But the sampling error is basically just randomly different depending on the pure chains. Good? Any questions? Nope. All right.
So that is one of the assumptions, right?
Right. So
we assume the sampling error is very random.
sampling error is random but patterned. So it's not haphazard. So random is different from haphazard. Haphazard is more of a, you don't even know the pattern. So you don't even know what you're gonna get basically. But if at least it's a random, it's decided by pure chance, but then it has certain patterns of what kind of errors will be obtained more often over the others. So for example, it is assumed that beta coefficient is the estimated beta coefficient follows a normal distribution or t distribution to be exact around the population beta coefficient, and then follows a t distribution around that population distribution, a population regression. So let's say this is 0. There is no linear relationship. Okay. And then depending on the sample, you can get either 1.2, -2, 0.3, -1, depending on the sample. Does that make sense? This distribution is called a sampling distribution. This is different from sample distribution. Right? Sample distribution is actual samples distribution. But this is a theoretical assumed distribution of beta hat. Why this is important and why am I talking about it so much? This because the standard deviation of sampling distribution is called standard error. Okay? So it means that standard error is about the patterned variance of sampling error. So if standard errors are really large, then it means that you don't really know. So basically, there's standard errors are really large, for example, and it would look like that, right? And there is a lot of chance to get, say, 4 as your coefficient, sample coefficient, even though the population coefficient is actually 0. So you never know, you're not really certain about your sample statistic. So standard errors are really about how uncertain you are about your sample statistic. In this case, it's a sample regression coefficient. Okay. So that's why they are really talking about standard errors a lot. Okay. And then if you divide beta hat by standard error, you would have the t statistic, and then t statistic is 1.96, then your variable would be significant at the 5% level. Does that make sense? I spent too much about it, but
So-
yeah.
So what else? There is like errors of sampling error.
oh, we're assuming that. This is
It's a
basically
normal distribution, right?
what
It's
Yeah.
a normal distribution.
Yeah, this is
sampling distribution.
t-distribution actually. Yeah. Anyways, yeah. So we are assuming that it follows a t-distribution with a good theoretical reason that we didn't really learn. If you want to derive this assumption, then you should talk to statisticians. Yeah, actually, statistics
And this for
department.
linear regression.
Oh, what?
And this for linear regression.
Uh-huh.
The sampling distribution is t distribution.
Yes. Yeah. Good. All right. Any questions? Nope. All right. Good. So now we're talking about OLS estimation. So I know a lot of you took Social Statistics 1 last semester. So how OLS estimation? How does OLS estimation work? What is the gist of it? Anyone? How does OLS estimation work? What is the gist of it? How would you summarize that?
So it's originally
Mhm.
least square estimations, and I remember it is using the least squares method.
Uh-huh.
So, yeah. It just minimize, minimize the square of
Mm-hmm.
what? Of the
It's fine. I can cover it.
of the error or variance. So
Yeah,
the
yeah,
standard errors,
correct.
Standard errors.
Mm-hmm. Yeah.
But yeah,
So this is actually ordinary least square, right? So it is basically finding a linear regression line based on this observation. How to find a linear regression line? It is a way of finding this linear regression line. This is one way of finding this linear regression line. Okay. So there are other ways to do that. But the most basic one, the most straightforward one is OLS estimation method. I'm pretty sure you're gonna learn maximum likelihood estimation as well, which is another way of estimating these lines, basically. But for now, OLS estimation is will be discussed in this section. So it's basically finding the linear regression line that minimizes this amount, which is basically residuals squared, and then you sum all of them. Okay, this is called so basically this is this residual squared and then you just sum all of them. Okay? Does that make sense? Yeah. While it is assumed that if you add up all of the residuals, then it'll be 0. Right? Does that make sense? So, obviously to predict, you don't want to draw a line where observations are right here, but you don't want to draw a line right like that, right? So that's why residuals should be 0 when they are added. Good? So they should be right in the middle in terms of the residuals. Good? But then the reason why we want to minimize this error squared, the sum of error squared, is that is to find the most efficient line, basically. Because we don't want to let regression line have a lot of unexplained parts of the variance of y. So as I mentioned, the primary purpose of linear regression is basically explain the raw variance of y, and then decompose the variance of y into explained parts and unexplained parts, right? And then you don't want to waste your regression line in unexplained variance. So you want to explain more of the variance of y systematically than just let a lot of theories loose. That's why. Okay? Does that make sense? Yeah. All right. According to OLS estimation, beta 1 hat, or the slope, is covariance of xy and variance of x, which is also noted as x. Okay. So I'll explain what is going on with that. So beta 1 is primarily the strength of covariance, correlation, basically. Right? Does that make sense? So, if they are they're strongly correlated, then the regression coefficients will be steeper. Right? But then it can be covariance can be really stronger when variance of x is larger. So we're just standardizing it in a way. Does that make sense? So in the verbal sense, basically it's the strength of association divided by some number to standardize it. Good. So really this the slope of a linear regression line really really reflects the strength of association in a way. Good. And beta 0 hat is y minus beta 1 hat multiplied by x bar. Y bar is the sample mean of y, and then x bar is the sample mean of x. So that's the formula of OLS estimation. All right, good. And then this is beta 1 hat's estimated variation or standard error. Because if you remember, this is beta hat, right? Depending on the sample, beta hat can be different, right? This is the standard error, right? So this is beta hat's standard deviation. So that's why it is noted as sigma hat of beta hat. Beta 1 hat. Any questions so far? No?
I missed the explanation about sigma.
Okay, yeah. So this is beta 1 hat, right? This is the sampling distribution. And standard error is the standard deviation of the sampling distribution, right? So this is really the standard deviation, but of this variable, beta 1 hat variable. This is a variable because it can vary depending on the sample, right? In this case, this is estimator. Estimator is a formula to calculate the estimate. So estimate is a number. So using this estimator or formula, that is this one, you are getting the estimate for a number, say 0.3. Good. In this case, it's a variable or an estimator in this case. And this is a number. It is also known as beta 1 hat, which is not really comfortable, really not convenient, but then it really depends on the context. Yeah. Yeah. Oh, sorry. Uh-huh. Oh no, estimate is a target of estimate in general. And then estimator is a formula to actually to translate the so beta 1 hat is an estimand when we're saying oh, this is the one we want to estimate. And then this is the estimator or this part is actually the estimator. It's a formula for getting the estimate for the estimate. Does that make sense? No?
Yeah.
Okay.
Or no?
Yeah. Yeah, sorry about that. This is beta 1. Sorry about that. Yeah, population coefficient is the estimand. And then this is what you want to get. This is what you want to get. And then estimator is the formula to get what you want. And the estimate is the number, actual number based on the sample. Does it? Am I making any sense? Or not? Sort of? I don't know. Good? Alright, good.
I make sure again. So standard error is the standard variance of sampling distribution, right?
Uh-huh.
And the sigma hat of the beta 1 hat
Uh-huh.
is what? Is the
So this is the standard error for the beta 1 hat.
so what is the sigma hat of beta 1 hat?
Yeah, this is the standard error for beta 1.
And what is
This
the standard error?
Oh, wait.
Standard error is a sampling. Is this
Sampling distributions, standard deviation.
so what is a sigma hat?
Yeah,
What is-
this is the this is standard deviation, estimated standard deviation. But then, so this part is theoretical, right? So you don't really, so technically it's a sigma beta 1 hat, right?
okay.
But then this is a theoretical distribution, right? So you are estimating it from your sample as well. So that's why it has a hat in it. Does that make sense?
Yeah.
Yeah, all right.
So why do we want to divide it by standard error? This formula
This one,
for the design.
divide beta,
This,
this one,
yeah, you just wrote there.
this is T statistic, right?
Oh, so that is not divided.
This is divided.
The one you wrote.
No, this is a number. This is a estimator.
Oh my god.
It's like one estimator.
I got it. So the one you wrote there is if there's a
No.
Because you wrote like
yeah.
numerator, denominator.
Oh, okay.
Yeah,
This one? Yeah, okay, sure.
That is equal.
Oh, I see.
yeah, so it's very confusing.
Yeah, okay, yeah. This is standard error. This is standard error.
Good.
Good. All right. So the formula for standard error is, what is this one? Anyone? We covered this just now.
It's a standard deviation. It's a standard deviation of error. Standard deviation.
Unexplained variance squared. Or variance of residuals squared. Good. How do you call what a different name of variance of residual is conditional variance of y. If I may repeat what we covered so far.
Well,
I'll explain it again. Yeah. We had raw unconditional standard deviation, right? Raw unconditional standard deviation. And then we're trying to explain what's going on with the y, right? And after explain what's going on with the y, we have conditional variance of y. Oh, sorry. Conditional variance of y or variance of residual. Okay?
Yeah.
Now that we conditioned on the linear regression line, we can call it conditional residual of y, or conditional variance of y, or variance of residual. They're all synonyms. Good. Any questions so far? Is it hard or is it difficult? It's all like 361 stuff, right? Yeah. Okay. Yeah. All right. So I'll explain the meaning of that. So this is standard error, and standard error is basically unexplained part of variance of y, which means that there's so much unexplained parts of y, you're not sure of beta 1 hat is a really certain statistic. Does that make sense? So do you see the story behind the formula? Like, so there's so many unexplained parts of y, and then you're not just sure about beta 1 hat is a really really a result of a sampling error or what's really happening.
So on the numerator, you said that's seven hat. Can you just say what's on the denominator?
Yeah. This is basically same as n minus 1 multiplied by standard deviation or variance of x, actually sample variance of it. Or for the sake of consistency, let's say that sample variance of x. Here. Yeah. So if variance of x is larger, then your standard errors get smaller in a sense. It's a purely because of the standardization purpose. I would not find a substantial meaning of it. But then, yeah, it's for the standardization purposes actually. Yeah. But then this part is important. N minus 1. N minus 1 is important. This is also a standardization purpose, but it gets important. If sample size is large, then what would it happen?
Standard error is smaller.
Standard error gets smaller, even though there's no difference in the unexplained parts. Even when there is no difference in unexplained parts. So that way, if the sample size gets larger, then standard errors are really get smaller, and that way, everything becomes significant when sample size is really large. Does that make sense? Because standard error gets smaller, then t statistic standard error gets smaller, then t statistic will become large, right? And you know, when t statistic is larger than 2, it becomes significant, right? So sample size gets really large, then you can just reject your null hypothesis no matter what. So that's the relationship between the sample size and standard error and significance, statistical significance. Does that make sense?
So what is sigma x hat squared?
What? This one?
Yeah,
This one?
yeah.
Oh, this is this is the variance of x, right? Sample variance of x, right? Sample variance, you know how to calculate sample variance? Do you know that?
I forget.
Okay. Sample variance of x is
Oh,
residual or distance, each observation's distance from the mean squared and divided by -1. So that's why.
so that one in the numerator is sigma hat squared. That's the upper one.
So this part is same as this one.
So these two are the sigma
These
hat.
two are the same things.
I mean sigma hat and the sigma x hat.
Right. This is the error terms significant, standard deviation. Residuals.
So how do you-
This is unexplained part of the regression. Okay. And this is x variables standard deviation.
So can you write the numerator just like the sigma?
Oh, what? Sorry.
Can you write the numerator sigma hat e just like sigma x hat?
Sure, I'll do that.
Oh.
Yeah. All right. Any questions? Nope. All right. Let's solve a practice question. I'll give you one question and 5 minutes to solve that. Okay. So the sample size is 100, and there is a linear regression line that is earning beta 0, beta 1, education, error term, where variance of earnings is 9, variance of education is 4, covariance of earnings and education is 3. And what would be beta hat? 1. And what would be standard error of the beta hat 1? All right, I'll give you 5 minutes. No, we'll get to that.
Oh,
But Does anyone some friend? We'll have like a 5 minute break after that. If you want to have it, yeah. All right, let's solve that question. So data hat 1. How does anyone can tell me the answer?
0.75.
Oh, what?
0.7.
Yes. How did you get the answer?
So it equals variance of owing an application minus the variance of education.
Yep. So covariance of earnings and education is 3, and variance of education is 4. So it's 0.75. Good. So the beta coefficient is really the strength of association standardized by some number. Good. That's the key takeaway from the question A, really.
Will you say that one more time?
Yeah, so covariance of XY means the strength of association, right? How strongly they are correlated with each other. And divided by some number for the standardization purposes. So, so the beta hat 1, or the regression coefficient, is really just strength of association. Mm-hmm. And then for the question B, how did you calculate that?
Yeah. So first you need to calculate the condition variance of y. So you can use the variance of y to minus the beta 1 square variance xy variance of the education, so you can
Sure.
the
Yes.
extent.
Uh-huh.
To use this, divide n minus 1 and divide the variance of education square.
Okay. Yeah. Sure. So as you can see, this is the formula for the standard error, right? So we do have n minus 1, right? Which is 99. And variance of x variable as well, which is 4. Good. So far, you're good to go, right? But the question is, how would you calculate the unexplained part of the regression? This is the key source of confusion in this question. To do that, if you really think about unexplained parts, unexplained variance, and then its meaning, then you can think about variance of y. You can really think about how to decompose the variance of y into explained parts and unexplained parts. Variance of y, or earnings, is variance of beta 1 0 plus beta 1, both hats, and then good. But then this is beta 0. This beta 0 is a number, so it doesn't do anything with the variance, right? No, a number doesn't have a variance, right? So we don't have to care about that. And we do know beta 1 hat is now 0.75 from question A, right? Squared variance of education, and 0.75 covariance of education and E, which is assumed to be 0. X and residuals are assumed to be 0 in linear regression, right? That's one of the assumptions for linear regressions, right? And variance of E. The unexplained parts of variance. And variance of education is 4, so you can plug in the number 4 right here, and then you can plug in the number 9 right here. Then you would have variance of E. And you can use that information to calculate standard error, which is this one. Now we know this part, and now we know this part from that.
Let's answer.
I can just tell you like how to get the answer, not because it involves a lot of complicated calculations and stuff like that. So does that make sense? No? Good. Any questions so far? Nope. All right, then let's take 5 minutes and move on to multivariate regression, dummy variables, and interactions, and nonlinear forms of independent variables. They should be really quick for each section, but I think I have more useful information to use. But if you can't stay, that's fine. It'll be recorded, so that's good. Yeah. All right, let's simplify. There's bread right there, so if you're hungry or anything, take some.
Yeah.
这个是碱啊，
It's what you need to focus.
对，我觉得是。然后这个square root 用吗？这个 square root 跟 square 就是要开根号的。如果好，这个要，所以这个是
Just like, you know.
我就是这样。
But you know this. Okay, you let me.
这个公式
Honestly. Honestly.
这
Like,
个
what was it in now?
其实也要
It's not like it's
这个东西长得要，这边又有一个这个
and you know. Okay, there's that.
Howard.
它这个到底这公式还是不是对的？
对。
那为什么他写的长得不太一样？
John.
对，因为
等一下，好奇怪哦！等一下，我要把它写清楚。就是这边给的公式是这个东西，
You find word or
Not too bad so far.
okay,
Next
that's
relevant plus is
这样
at
对不对？然后他第二页给的公式是什么？
开始过，
哪一个啊？
前面少了一个根号，
你觉
前面
得怪
少
怪的？
一个根号，这要少加个根号，
这个要加个根号。对对
这样
对
子实际上写在一堆。
那要不跟他说一下？跟他就他前面少个开根号。跟他说一下。那这个快乱了。所以说这个东西是什么？这个嘛，
就是那个无差项的标准差。
这个嘛，还有到底是什么东西啊？符号那么混乱，所以这个 sigma 还有指的是什么？就是这个
其实
是这个东西吗？这个吗？
对，
这样要开根号的了，因为没有
就是不是五分啊，
是这样吗？是这样吗？
对啊，他用的都是量子力学的标准，
sigma head 这个是什么东西啊？它的
因为它是一个
它是那个回这条这个是你的哪什么东西？所以我现在有搞不太懂这个还有。不同东西对不对？
That's all. I can see your friend. No.
是这样起来对。
Yeah.
所以这个需要这个然后这个东西要在开根号，然后就可以带到这个系。
这是通过样本误差计算出来的标准差，
对啊，
对吧？
标准误差还有 standard error。
标准是个标准误差是个标准名字，当时我看标准误我也是觉得很操蛋。
后来用中文就用讲，这中文奇怪。
这个就是样本误差项的标准差，
是哪一个啊？
就是样本回
这个吗？
归方程
是这个吗？是你今天跟我拿的吗？
会有不同，因为这是总体的，这是总体的，这是总体的，这是总体的。你不要管条件不条件，它是怎么呢？它是有一个总体方程，是有一个总体回归方程，有一个样本回归方程。总体回归方程我们是得不到的，因为我们永远只能得到样本。That'll be fine。想太多了，你真的想太多了。没人在乎。
This is yours.
I absolutely didn't know.
So you have this original. EI. You do that for the whole object. And then this is 1, 2, this is 2, this is 3.
Yeah.
It's a notation.
You are using a variable,
That's just the
all variables.
Since I have,
Calculate the variance of this variable. Do you know how to calculate the variance?
So this is.
This is the unexplained variance. Reggie was.
Residual variance.
So this is the unexplained variance.
So that's the.
For what?
There's different numbers. So that's the variance from. So it's-
Yeah, and then this is the unexplained part of the variance of y. Just x variables.
Oh, John.
X variables. X variables.
Yeah, so it's just like.
Yeah. There's a split.
And this.
Oh, okay. Sorry about that. All right. Let's start again. Before moving on to multivariate regression, linear regression, let's talk a little bit about Euler's regression's assumptions. Okay. So assumptions, it'll be really brief because it'll be covered in a future lecture of Source 362 again. So I'll be really brief in that sense. Okay. So the first one is linearity, which is obvious. So there is a linear relationship between y and x. And the second assumption is there is no covariance of x and e is 0. So covariance of x and e is 0. That is another assumption. So this is not necessarily needed for, this is required for linear regression in general, not the estimation per se, estimation of beta 1 hat and whatnot, but just linear regression for the linear regression line to make sense, for a linear regression line to make sense. And the third one is no perfect collinearity, which will be explained in a minute. I'll explain what that means in a minute. And the fourth one is homoscedasticity. I'll just late errors are not related to each other. And errors are normally distributed. These three assumptions are summarized as EI follows normal distribution of this one, IID.
Sorry, that says that the EI follows normal distribution
Of normal distribution of 0, comma, sigma hat, sigma squared, which is the normal distribution's mean is 0, and the standard deviation is sigma. and IID is independent and identically distributed. I'll explain what that means in a future lecture, in a future section. Okay. I'm pretty sure there's a chance that I'll cover this part. Okay. All right.
Wait.
Oh, if you watch the YouTube clip, then you'll find with that, and then I'll cover it again in a future section anyway. So don't worry about it. Don't worry too much about it. So let's go to multivariable regression. Multivariable regression. So this is actually different from multivariate regression. Just this is on FYI, but this is not multivariate. Multivariate regression has more than one outcome variable, more than one y variable. So there are like multiple y variables in the regression line, which is exemplified by structural equation modeling, which is typically taught in educational psychology department. But this is not what we're gonna cover in this class, but I'm just letting you know that regression line with more than one independent variable is called a multivariate regression, a multivariable regression, okay? Some people confuse that, so just to make sure you're using the right term. So now, y variable is the combination of beta 0, beta 1 hat, beta 2 hat, x2, ei. Okay? And the marginal expected value, or just the expected value of y, is simply the linear combination of these values. Which is 0. Good. This is the unconditional or marginal expected value. And the conditional expected value is now given given 1i, comma, given 2x2i. So we're fixing the values of x1 and x2. Good? So yeah. So basically, okay. Good. This is the conditional expected value of y, or it is same as the predicted value of y given x1 is x1 and x2 is small x2. So this is the predicted value of y given x1 is certain number and x2 is certain number, any certain number. which is, the regression lines. It is also noted as y hat, as we saw earlier with the bivariate regression model without any just one independent variable. Good. I add i's, but anyways, it's not important. And then variance of yi, or marginal variance or unconditional variance of y. This is before condition, right? Good. I'll just omit all of the i's. So by assumption, x1 and e are 0, and x2 and e are 0. Again, if you run the regression, and then if you actually run the correlation between x and the actually obtained error terms, then correlation would be 0 by design. Okay. It is not because of what is really going on. It is not because the assumption is right. Right? The actual numbers are obtained based on the assumption. This is an assumption again. Okay. So the meaning of this equation is that variance of y, or raw variance of y, is decomposed into explained parts, or relationship with x1 variable and relationship with x2 variable, and correlation between x1 and x2, and unexplained part of the variance. So this part is really important. Good. Variance of y is decomposed into the relationship with x1, relationship with x2, and relationship between x1 and x2. This means there should not be perfect correlinearity. If we go back to the issue of collinearity, then so basically they are perfectly explaining each other. Then this part will be basically really large. Will be really large, right? Does that make sense? So it'll be absorbing. So unexplained parts will be same anyways, regardless of whether they are correlated or not, right? Because you're using two variables in the same anyways. So let's think this is fixed for now. But then if their correlation is too high, then you don't absorb all of the this part. Absorb the variance to here. So all of the explained parts of the variance of y will be absorbed to here, to this part. And then, as a result, correlation regression coefficients will be really small as a result. This will be more clear. This will be clearer when we talk about standard errors. Sorry about that, but let's just If you don't understand what I mean, that's fine. I'll explain in more detail with the standard errors. Okay. Good. All right. And then same if you have. Oops. The conditional variance will also be variance of E, just like the regression with only one independent variable. This is the conditional variance of y. Conditional variance of y, or sigma E hat squared. All right, good. And I think we covered how controlling works in the last section. So let's say, let's move on to actual calculation of the coefficient and the standard errors formulas. Okay, if you understood the previous part. Okay. So how do you get the beta hat one? When someone controls for x2. Anyone? How does controlling work? Anyone?
You still need to use the least square method.
Right, true. But I'm asking more of how controlling works rather than just OLS estimation.
Can you remember the matrix calculation of this?
I'm not looking for matrix approaches actually. Matrices should be used in the calculation of OLS estimator, but I'm asking more of a basic mechanisms of controlling, right? We cannot just like say, yeah, matrix will cover that, and we don't know how that works. So matrix covers all of that, so we really don't know how that works. That's not what we want, right? So we really should be able to explain what is going on verbally when we explain our results or regression results to, say, the public really. And then when one might say, how do you control for certain variables when the sample has different characteristics, basically. So for example, how do you know the racist effect on income, net of gender, when everybody's gender is different. How do you do that? This sounds nuts, right? This sounds weird, right?
I think I covered that last section, so in the last section. But how do you do that?
The first
Oh,
step.
yeah.
Okay.
So you need to, you still need to minimize the error term square.
Uh,
So you should-
Sure, but there's more of a OLS estimation. Still, right? This is more of an estimation. I'm asking more of a how controlling works.
Okay. So
Yeah, can you explain more about that? Sorry for interrupting.
I mean, you may. So I remember the first natural is to use Lagrange. The Lagrange naturals to. Or the second one is to calculate. I forget the English expression of that natural. So you should. Sorry.
Okay, yeah, that's fine. The first step is basically regress x1 on x2. Okay, and the second step is to regress on y, regress y on E1, where you got E1 residuals from this regression. Does it make sense?
Yeah.
So x1, x2, x1 is, in the first step, x1 is considered as the outcome. And then you have the regression line, right? And then you would have residuals for all observations. And then you are making a new variable, E1, out of these residuals, and then regress y on E1 to get the beta 1 hat. Why is that? That way, you are using the residuals from this regression, right? So you are deleting out, decomposing out the influence of x2. So this is the unexplained parts, right? So explained parts of what x2 on x1 will be decomposed out when you are using E1. Does that make sense? No? All right. So how should I explain it? So the purpose here is basically to get this one, right? And you want to really delete out this x2's influence when calculating the beta 1 hat. That's linear controlling, right? Does that make sense?
Yeah.
And then what?
Sorry.
Yeah, no, it's fine. So if you run the regression of x1 on x2, then you are explaining x1 with x2, right? And then unexplained parts will be unexplained variance of x1 when after x2's influence on x1 will be deleted out. So that way, we didn't learn that too specifically, but this relationship is deleted out when you use E1. So the influence of x2 is not there. You can just look at the beta 1 hat. That's how you that's how controlling works in linear regression. Does that make sense?
So
Sort of.
what if x1 and x2
Uh-huh.
perfectly correlated
Correlated with each other.
in each
Then
other? There is
beta
no-
1 would be not really calculated.
Yes, because there is no residuals.
Right, no
First
residuals.
step.
All zeros.
All
It's not a
zeros.
variable anymore. So it won't be calculated. Good.
Is that multicollinearity?
Yeah, if perfect collinearity is that x1 and x2 are same, and multicollinearity is x1 and x2 are so strongly correlated with each other that it's almost not there, not exactly there yet, but not exactly there, but it's really strongly correlated that they absorb each other's variance. Basically. I'll explain in more detail with the standard errors part, but yeah. Any questions?
So the first step is to delete the influence of x2,
Yeah, x2 on x1
and after doing that, it will remove the
Right.
x2.
by using E1 as the predictor. Now you are deleting out x2, influencing x1, and after that you're running the regression. So that's how you can claim that you are controlling for Genders effect when you're estimating Bayes' effect on income, which sounds weird, but it's a one way to control for, or one way to condition on other variables to estimate one Bayes effect. Good. A lot of people don't teach that, and then I don't understand why. I think it's really valuable to understand what's going on with the controlling, and then just people think that if it's controlled, everything is same, but it's not really the case. You know, it's one way to pretend as if everything is same, even though it's not. So so you should be able to keep note on that for this class in general, and then for your career when you're doing quantitative research and use regressions.
But you can only use in the equation of only two variables. We have more than two variables.
Yeah, if you have more than two variables, you can do that. Do the same thing, right?
But maybe the x2 and x3 may be correlated with each other.
Assuming that they're not perfectly correlated with each other.
But we can have the macros, particular method, or other method to calculate this. Yeah, maybe.
No, but the macro will do the job for you. But then this is like you really don't want to say that the macro will do the job for you, so we don't really care about how that works, right?
Yeah, that,
You really want to really understand what's going on with the regression models you're using, and then you should be able to keep notes on what you're arguing for, and then you're claiming based off of that.
but we can calculate with our hands if the variables.
Right. Yeah. The macros will do the job for you, but then that's not my point. My point here is that you should be able to understand what's going on and what it means by controlling to explain what your results are, what results suggest. Okay. All right. Good. We don't have a lot of time, but I'll try to. Okay.
45 minutes.
We will cover standard errors when you control for other variables. x2 is formula looks like this. It's basically same, but with the added component of here. 1 minus R12 squared. R12 is the correlation between x1 and x2. Okay? If correlation between x1 and x2 is 1, where they're perfectly correlated, then 1 minus 1 becomes 0, right? Then this part becomes 0. Then the standard errors will be infinite, or negative infinite, actually. Good. So that's why perfect collinearity is not allowed in linear regressions. And if this is 0.9, which is really high, then standard errors will be increasing drastically. If not, it's not infinite. Good. So a classic sign of multicollinearity is drastically large standard errors, actually. So if you want to really suspect there's a collinearity going on, then you should be able to really think about how standard errors are affected in terms of inflation. Good. Okay. And we covered decomposition of sum of squares, which is not too difficult when you understand what's going on in the regressions. Okay? So basically, it's saying that so this is the sum of squares. Or TSS. Okay? So this is the raw variation of y variable. Even before average or something like that. And this is y bar, which is the sample mean, right? The difference between predicted value and the sample mean, which means this is y bar, right? Before running the linear regression, we just expected that y would be here. That's the definition of y, right? Expected value. So without running the regression whatsoever, you're just saying that what do you think y would be? Just guess that. Then you would give the expected value as your answer, right? Because you don't have any regression or prior information whatsoever about y. Just you would give the mean, basically. That's the expected value. What value would you expect before running the regression? But then, after running the regression, based on x's information, based on this value, you are predicting that, oh, this person would have this level of predicted value. Okay? So now we have this amount of understanding. And you could square it, and then you do the same thing with the all observations. Then you would have model sum of squares, which is explain the variance of y. Okay? And the rest is SSE, or unexplained variance of y. Sorry, I'll lay out the abbreviation. Total sum of squares, model sum of squares. This is sum of squared errors. All right. Good. And R squared is basically MSS divided by TSS. That's why you, when you interpret R squared as 60% of the total variance or explained by the model, and that's why. R squared is basically explained parts of the variance divided by total variance. All right. Good. Any questions? Nope. All right. I was going to go over a little bit about F-tests and whatnot, but this is not really important in Statistics 2, so I'll just gonna skip that. So this won't be too important in passing the class, but I'm happy to like teach you what that is if you come to my office hours and whatnot. Office hours or everything. So so if you have questions about that, you should definitely let me know. Okay. All right. So did you all have this data outputs? Even if you don't have the outputs, that's fine. I'll just like lay out the regression line basically, so that's fine. So the regression outputs, there is expression called bivariate regression and multivariate regression. They're wrong. They should be called multivariable regression. Yes, they should be corrected. It's so catchy that like I make mistakes a lot about that, but they should be corrected. All right. Let's move on to the dummy variables. Okay. So for dummy variables and interaction variables, I think it's best to just get an experience with while working with the state outputs, really. So in dummy variables related outputs, so it was reg, prestige score, occupational prestige score, one's income, and female dummy variable. Okay. So regression equation is and then B2 hat was 2.288. Let's say 2.3 for the sake of simplicity. So the Y variable is the occupational prestige score. Then how would you interpret this coefficient? Anyone?
On average,
Yeah.
female has 2.3 higher prestige than male.
Right. Yes. You always want to make sure that you mention the reference category when you mention when you interpret dummy variables effects. Okay. So female means one is female and the male respondent becomes 0. So compared to male respondents, women have 2.3 higher occupational prestige scores on average, and the p-value is less than 0.001, which means that the significance, it is significant at the level of, say, 0.1%. Okay. Good. All right. Any questions about that, or? Nope. All right. And now, we have interaction variables. Now we are interacting with race here. Race is for person of color, it's 1, and oh, sorry, not true. For African Americans, it's 2. Sorry, before white is 1. African American is 2, and the other is 3. Okay. And then the regression results suggest that female let's say black. Other female black, and then 1.0 female other. Okay. So in this case, what is the strength of association or effect size for women. How would you interpret the results? If someone asks, what is the effect of female variable? How would you answer that question?
And it also depends on the race.
Right.
We have the relation.
Yeah, the correct answer is it depends on someone's race. Okay, good. So if someone's someone's race is white, then the effect of female compared to white male is 1.8. Right? We are assuming white, right? Good?
Yeah.
So these will be zeros. And white females have 1.8 higher scores on average. And for black male, it'll be negative 2.7 compared to white males. Does that make sense? So beta 0 here is the average score of white male when our or someone's income level is 0. Good? Because all of them should be 0 to have that average as the intercept. Does that make sense? Any questions? Nope. All right. You can also if you're a black female respondent, then it'll be 1, 1, 1, right? And the other would be 1, 0, 0. So the compared to white male, female black's effect is 1.8, negative 2.7, 2.5, plus 2.5. How about white female? Black female is this is 1, right? And this is 1. Okay. Does that make sense? Any questions or about that or? Nope. All right. If you don't have any questions, yeah. I think it's supposed to be until 8, but I think it's all the necessary things we have to cover for basically to pass Sostrix 2 and the background knowledge for Sostrix 2. So let's then I'll see you next week then.
You share the